So here we're going to look at how the continuous monitoring method can be used alongside concentration time graphs to determine the order of reaction with respect to one reactant. So in this particular example, we're going to try to measure using the continuous monitoring method and concentration time graphs the order with respect to reactant A. So imagine we've got A and B reacting to make some products. Okay, so we'd need to start with known amounts of A and B, and we're going to ensure the concentration of only A is changing so that only A can affect the rate and so that we can determine the order with respect to A. And to do that, we need to keep the concentration of B much larger than the concentration of A. And the reason for that is, if you imagine, let's just take an example up here. If you imagine that you start with 1 mole of each, and then after a minute there's 0.9 moles, or there'd be 0.9 moles of B, and then there'd be 0.8 moles of A, and there'd be 0.8 moles of B, because they're in a 1-to-1 ratio. And so you wouldn't know whether the effect that you were measuring was due to A or B, because they're both changing in exactly the same way. Now, if I change that though, and instead of having 1 mole of A and 1 mole of B, I have 1 mole of A and 1,000 moles of B, so it's much larger. Then after a minute, say this has gone to 0.9, this will be at 999.9, which to 3 significant figures is still 1,000, and then this has gone to 0.8, this would be at 999.8, and you can see that B is remaining effectively the same number, as we say it's effectively constant, whereas A is changing significantly. So A has decreased by 20%, but B has barely decreased at all. So by using our one concentration much larger than the other, we can keep one of our reactants effectively constant, which means we are measuring the effect on rate of the other one only. And therefore we can say it's not going to B, the big one, is not going to affect rate, and only A affects rate. We say it's pseudo zero order, it's acting like it's zero order. Then what we would need to do is, now that we've set up an experiment where we can measure the effect of A on rate, we need to find a way of measuring concentration of A at different times during our experiment. Now that's quite tricky because the concentration of A is decreasing continuously throughout the experiment. So we would need to find a way of measuring it at a set time. So at 5 seconds, 10 seconds, 15 seconds. So it could be that we could measure the volume of a gas produced. So we just have it set up with a gas syringe, and we can measure the volume of gas being produced over time and look at that graph. And that volume of gas produced would be directly linked to the concentration of that product. We could measure the pH of the solution with a pH meter, because pH is directly linked to the concentration of hydrogen ions. So if we were trying to measure the concentration of hydrogen ions, this would be a perfect way to do it. We could measure the change in mass. Maybe a solid was reacting and the mass of this mixture was changing, and we could use that to determine concentration. Or, nice and easy one, we could measure absorbance of coloured solutions, so using a colorimeter. So solutions that are coloured, like potassium manganate, it's very purple. It would absorb visible light, and as its concentration decreases, it would absorb less and less visible light. The absorbance is directly proportional to the concentration. So we could plot a concentration time graph by just plotting an absorbance time graph, and we'd get the same effect. Now, if none of these methods is going to work, these are all able to be done continuously, we would need to stop the reaction. So quite often we like to measure concentration by carrying out a titration, but titration takes time. You've got to pipette and fill your burette, and you've got to add dropwise at the end point, and so you can't do it at a very specific time. So you need to stop the reaction at the 1 minute interval and the 2 minute intervals so that you can measure the concentration, and we do that by a process called quenching. So quenching is a way of stopping. So you would start your reaction off, and then when it got to 1 minute, you would quench it, and you can do that nice and easily by plunging your reaction mixture container into an ice bath, and by reducing the temperature significantly, you slow the rate to almost stopping. Very few particles have the activation energy, and therefore the reaction stops at that time, and you can then measure the concentration. So using an ice bath is a quick way to quench, to stop a reaction at a certain time. Once you've done that and you've got lots of concentration readings at lots of different times, you can plot a graph of concentration against time and use the graph to determine rate. So remembering that rate is going to be the gradient at that particular time. You can find the concentration at that time by reading the y-axis at that time and the x-axis values. So you could go to an x-axis value, read off the y-axis to find the concentration at that time, and measure the gradient at that point as well to get the rate at that time. And then you could plot a rate concentration graph to look at the shape, or you could just compare a couple of different concentrations and their rates to see if you could figure out the order. So I've got an example using that here. It's got bromine and methanoic acid reacting, and we're using a colorimeter, and that is because bromine is like orangey red depending on the concentration, and the products are all colourless. So during the reaction, it's going to be absorbing a lot of light when there's a lot of bromine, and as the bromine concentration decreases through the reaction, the absorbance on the colorimeter is going to decrease, and so the concentration, we can see it decreasing over time. And here's a graph, and we're going to have to draw on this graph. It says at time 0, determine the concentration. So if we go back up, and remember that for concentration, we're reading the y-axis value at time 0, so at the start, it's 0.010. Okay, and it says draw a tangent to the graph to calculate the rate. So we're going to need a ruler for that. I'm going to just temporarily rotate the page so that I can see the whole graph on the page. I will turn it back in a second. And we're going to line our ruler up with the graph at time equals 0, so at the very start, and we're going to draw a tangent to the curve at that point. So I'm just going to do that now. Okay, I'm going to take my ruler away. We'll rotate it back round. And so then we can measure our gradient. So remembering that our gradient is dy by dx. Now I drew a really nice big triangle, so I'm all the way to the axes at both sides. So I can say that my dy is 0.01 minus nothing from that top point there to the bottom of my triangle at the origin. And my x-axis values are 230 minus nothing. So I can work out my gradient. Just over 230. Let's call it 232. We're getting 4.3 times 10 to the minus 5. Okay, and then it asks us to repeat at 300. So I'm going to repeat this at 300. So I have to go up to 300. I'm going to get my ruler out again. I'm going to draw a line across at 300. So I'm just going to do that first. I can read off the y-axis value as 0.0034 and write that in. And then I'm just going to rotate the screen again so that I can draw. And we're going to have a look at what we are measuring at that point. Get rid of our ruler again. So we're going 0.0034 0.65675. Again, I'm going down to the origin because I've drawn my triangle nice and big. Over 605 1.12 times 10 to the minus 5. Okay, so I've got 4.3 times 10 to the minus 5 and 1.12 times 10 to the minus 5. And then we can compare these two. Now remember, this is experimental results, so it's not brilliant. So what's the changing factor here? So the bottom line, 0.034 divided by the top line. So that's times by 0.34. And then we do the same here, the bottom line, 1.12 times 10 to the minus 5 divided by 4.3 times 10 to the minus 5. And we're getting 0.26. Now we can see that that is not perfectly first order, but we can also make some scientific interpretation of this. If it was 0 order, then the rate would be identical. It's definitely not close to identical. If it was second order, then the rate would go up by 0.34 squared, and if we applied that, we'd be looking at something times 10 to the minus 6, and it's definitely not that either. So if we think about these two numbers, it's 0.34 and 0.26, and because it's an experiment and we can't rely on them that well, we think, well, actually, if I give them to one significant figure, 0.34 is 0.3, and 0.26 rounded to one significant figure is also 0.3, and so we'd say that when our concentration of bromine is increased by 0.3, our rate is increased by 0.3, so our power must be a 1. We'd say the order with respect to bromine is first order. This is how we could use some experimental graph data for concentration against time to determine order.